So in the previous video, we talked about alkanes. In this video, we're going to be talking about alkenes. All right, so what an alkene is, it's a carbon chain that contains a double bond. All right, so one thing right off the bat, alkenes are a lot more reactive than alkanes. All right, and so if you were to look at a carbon-carbon single bond versus a double bond, there's nothing really that would stand out immediately that would say, hey, this is a lot more reactive. All right. But what you've got to remember is that even though we draw it as if these two bonds right here are identical, remember that one of these bonds stands for the sigma bond, all right, and one of them is for the pi bond, all right. And what the pi bond is, that's where you have these p orbitals that are side by side, and you get a little overlap of the electrons, a little sharing of the electrons between those lobes, all right. So the thing is that the pi bond is not nearly as strong as the sigma bond. All right, and a way that we know that is if you take a look at what the bond enthalpies. All right, so this is just some data that I got from the data booklet. Okay, and in case you're wondering, this data is located on table 11 of your data booklet. So what the bond enthalpies represent is the amount of energy required to completely break the bond. All right. So the thing is, it's not just the amount of energy required to break one of the double bonds. It would be the amount of energy required to break both of them. All right. So here's the thing: if both of these double bonds were, or both of the bonds in the double bond were just as strong as one of these sigma bonds, you would expect this right here to be twice as large, all right, because that would mean it would take at least twice as much energy to break those. But notice that this number is not quite twice as large as this sigma bond, all right. So what that indicates is that the sigma bond within a double bond is relatively strong, but the pi bond is not nearly as strong as that sigma bond. So one common type of reaction that alkenes are very well known for undergoing is what are called addition reactions. All right. So there's four major types of these that we're going to go over. But first I want to mention what is meant by an addition reaction. All right. An addition reaction is any reaction where the entire molecule that you're reacting with gets added to your substrate, all right, or the alkene in this case. All right, so what I mean by that, if you take a look at this alkene, and this is the simplest alkene that there is, this is ethene, or it's more commonly referred to as ethylene. All right, you'll notice it's got 1, 2, 3, 4, 5, 6 bonds. All right, you've got 4 hydrogens there, but we're going to react it with H2, or a molecule of hydrogen, and you'll notice that there's 2 hydrogens there and there's a single bond. All right, so between these 2 molecules right here, you've got a total of 7 bonds, 6 from the alkene and 1 from the hydrogen. Okay, and if you look at the product right here, you'll notice that there's 1, 2, 3, 4, 5, 6 hydrogens, and there are a total of 7 bonds. All right, so essentially what that means is that all of the parts of this hydrogen molecule, both the hydrogen atoms and the electrons that were in that bond, have been added to this molecule. All right, in case you're wondering, the 2 hydrogens that are in this, one of the hydrogens you could think of as being this guy, and the other one would be this guy, and these guys down here would be the original hydrogens that were part of the ethene. All right, so whenever you're doing a hydrogenation, the way you're going to conduct this is you react some hydrogen with this in the presence of a palladium catalyst, and this is really not that high-tech of a reaction. Okay, in fact, when you're doing one of these reactions, this is essentially what you're going to do. You're going to have a round bottom flask. You're going to have your alkene dissolved in some solvent, and it looks kind of black down here, all right? And that blackness, the palladium comes on, generally comes adsorbed onto this charcoal type material, all right? So that's what gives it that black color, all right? So And all you have to do is you literally just take a balloon, you fill it up with hydrogen, and you pop it on top of the flask. All right. You'll notice that there's a little apparatus right here. Essentially, this is just a vacuum pump, and before you put the hydrogen on there, you try to suck out as much of the air as possible, so that when you add the hydrogen balloon, essentially you're going to have all hydrogen on top and none of the oxygen and nitrogen that would come from the air. All right. So one of the neat things about this reaction is that hydrogen is a reactant. All right. And if hydrogen is getting consumed as part of this reaction, one thing that you'll see happen is that this balloon actually gets smaller over time. All right, because it's getting absorbed by the molecules down in the reaction. So one of the most common uses for hydrogenation is in the preparation of vegetable oils. All right. If you've ever looked on the side of an ingredient and it says partially hydrogenated vegetable oil, all right, what that means is that the oils have what are called fatty acids, and a lot of these fatty acids have double bonds in them. All right, and if you hydrogenate that vegetable oil, essentially what you're doing is getting rid of some of those double bonds. You're converting some of those double bonds into single bonds, and what's known to happen is that that type of oil is going to have a longer shelf life than if it's got a lot of the double bonds in it. Okay, the next addition reaction is going to be what's called a hydration. All right, and when you think of hydrate, you think of water. All right. One thing I want to point out: don't get hydrogenation and hydration mixed up. Notice that hydrogenation has the entire word hydrogen in it, but hydrate, right? Remember the hyd would be for the hydrogen, and ATE, that's generally going to be whenever you have oxygens in a molecule. All right. So when you do this, you're essentially adding a water molecule. All right. So notice by comparison, one of these carbons now has an additional OH, and the other carbon now has an additional hydrogen. So you've literally added H2, there's two new hydrogens, and an O. And where did those things come from? They came from a water molecule. All right, so in order to do this, you have to do it in the presence of an acid catalyst. So generally you're going to have to add some sulfuric acid, but this is a fairly simple reaction. All right. Next is a hydrohalogenation. All right. So if you treat an alkene with a hydrogen halide, all right, in this case we're going to do hydrobromic acid or HBr. All right. You'll notice that you add a hydrogen here and a Br here. So you've added this entire molecule to that double bond. All right. And the last one is a halogenation, all right, and these are either known by a bromination or a chlorination, all right. So notice I'm using Br2 here, and when you do that, you end up adding a bromine to one and another bromine to the other carbon, and notice that in all of these cases, the double bond is no longer present in the product, all right. Okay. So I didn't write it down on the notes here, but you might want to make a note of this out here. This bromination reaction, because this reaction happens whenever you have an alkene, this is used as an indicator to test whether there's an alkene present in a molecule. All right. So bromine is kind of a reddish color. All right. And if you add a little bit of bromine to some solution, if you see that reddish color disappear, essentially what that means is you're adding bromine to a double bond. There had to be a double bond there to react with the bromine so that the color of that bromine disappeared. All right. So if you add the bromine and the red color stays, that means that there's no double bonds in the thing that you added it to consume it. All right. So one last thing, and this is an HL topic, the mechanism for this reaction. All right. So we talked in the previous video about homolytic versus heterolytic electron movement. Notice when I'm drawing these, I'm using that double-headed style of an arrow. All right, and what that means is that both, like a pair of electrons, is moving when I'm doing this. All right, so what's going to happen first is the electrons in the pi bond of the alkene are going to attack what's called attack this bromine right here. All right, and the 2 electrons in this bond of the bromine molecule are going to go onto this bromine. All right, that's going to create a bromide ion. All right, and notice I didn't draw the electron pairs around this bromine right here, but you would expect there to be 3 electron pairs on that bromine. And when the electrons go onto that bromine, that creates a 4th lone pair on that bromine. All right, so I've actually drawn them in here. All right, so this would be a bromide ion. So one thing to notice, when the electrons from that pi bond attack that bromine, it's like they're staying connected to this carbon right here, but they're no longer attached to this carbon. All right, so that's why we have, so this is where those electrons were. All right, so since these electrons are no longer bonded to this carbon, there's now a formal positive charge on that carbon right there, and that's what I've drawn right here. So that bromide ion is going to be attracted to that positive charge on that carbon. All right, and the lone pair, you can show it like this. You can show it attacking that carbon, and what that indicates is that we're going to create this bond right here. All right. So one thing I want to point out is this is technically not a correct mechanism. So I don't want to get into the exact reasons why, but you'll learn if you take organic chemistry that with ethene it would not proceed exactly this way. All right. So moving on. So in all of these addition reactions right here, we had one single molecule reacting with another single molecule to make one relatively small addition product. All right. So one other thing that can happen is that essentially you can start a chain reaction where one alkene ends up adding to its neighbor. All right. So I know this looks a little busy, but essentially what it is 3 ethene molecules drawn side by side. And what I'm showing here is if the electrons here, one of the bonds from the double bond were to attack this carbon right here. These electrons here were to attack this carbon. These electrons here were to attack the carbon right next to it. And essentially this would just keep on going. All right. You would end up having this chain reaction event happening. And when this occurred, okay, remember when these electrons right here go and attack this carbon, they're going to stay attached to this carbon, but they're no longer going to be attached to this carbon right here. So what was a double bond is now going to be a single bond. All right, so where did those electrons go? Those are now the electrons that are forming the bond between this carbon and this carbon. All right, so that's what this bond is right here. All right, so if this thing keeps on going, notice that there were 2 hydrogens attached to each of the carbons before. There's 2 hydrogens attached to each carbon here. It's just that they're now all linked together. All right, so you end up creating this really long chain. All right, and this can go on for thousands, if not tens of thousands of units long. All right, and this is what's called a polymer. All right, so the name of this particular polymer is polyethylene. All right, you can also call it polyethylene. And if you ever look at the recycling symbols on the bottom of plastic, if you either have a 2 or a 4 plastic, that's going to be polyethylene. Okay, one thing I want to mention is, like, whenever you're doing a polymer reaction, the molecule that you start with before it polymerizes is what you call a monomer. All right, so 2 other important polymers are one made with this molecule right here. This is called vinyl chloride or chloroethane. And when it polymerizes, it's going to make polyvinyl chloride, which is known as PVC. All right, that's number 3 plastic. If you're going to use standard IUPAC nomenclature, you would call it polychloroethane, but most people are going to call it polyvinyl chloride. All right. Another important one is this guy right here with the 4 carbons, and that's going to make polytetrafluoroethene, otherwise known as Teflon. All right. One thing I want to point out about this is that this reaction was invented completely by accident.